Hello everybody, my name's Andrew Knight. I'm a veterinary professor of animal welfare at the University of Winchester Centre for Animal Welfare, and I've been asked to talk to you about the use of animal models within scientific research, not as models for the same species, but as models for human beings. Now, this is obviously a very controversial subject. When we consider whether animal research protocols ought to proceed, we tend to use a utilitarian framework to weigh up the harms and benefits. The beneficiaries, as I said in our case, are going to be human patients. The harms are usually experienced by the animals that are being used. This kind of utilitarian harm-benefit analysis is fundamental within legislation and policy governing animal use internationally. The major European directive governing laboratory animal use is a good example of this. It requires the scientific or educational validity, usefulness and relevance of each use of an animal to be carefully assessed, and specifically requires the likely harms to the animal to be balanced against the expected benefits of the project. So, how useful then is animal research for advancing human healthcare? There's certainly plenty of claims about the utility of this research in scientific literature, typically by animal researchers. Some of these claims are very strong, as you can see, citing the complexity of laboratory animals and the purported inadequacy of alternatives to laboratory animals. My favourite really is this one, the claim that medical progress would be severely maimed by prohibition or severe curtailing of animal experiments, and that catastrophe would ensue if this occurred. There are, of course, also strong claims on the other side of this argument, and historically, arguments about the usefulness or otherwise of animal research have depended upon historical accounts of the contribution of animal research to development of cures for various human diseases, and these are often contested and also don't give us much information about what might have occurred had those scientific resources been redirected into other fields of research, such as clinically oriented research. They also rely upon the citing of examples in which animals and humans have similar outcomes or different outcomes, which is concordance or discordance. And there are plenty of examples to cite. There have, of course, been a range of drugs that cause serious side effects or death in some laboratory animal species that, if they had undergone modern animal testing, would never have made it through to the marketplace and be available for the treatment of human beings. There are also another group of drugs that have been released onto the market after passing more rigorous testing in animals and very limited testing in phase 1, 2 and 3 clinical trials on humans, that after release into the marketplace and reaching a much larger and more diverse patient population are found to have quite serious human side effects. TGN-1412 was a monoclonal antibody being developed for the treatment of arthritis and other inflammatory conditions that caused multiple organ failure, unfortunately, in all 6 human volunteers that were first given the drug in 2006. And you can see one of them in the picture. Sadly, this young man had the peripheral vasoconstriction and lost some of his fingertips. Vioxx was another anti-inflammatory drug withdrawn from the global marketplace in 2004 after going through extensive animal testing, in which it was found to be safe and even beneficial to the heart, but once released into the human marketplace, it caused 140,000 heart attacks and strokes and at least 60,000 deaths before being withdrawn. And there are many more of these sorts of examples. They're so common, in fact, that adverse drug reactions were recorded as being the 4th to 6th leading cause of death in US hospitals over a 30-year time frame, and they kill over 10,000 people annually in the United Kingdom each year. Now, the trouble with providing these sorts of historical accounts or lists of examples in which animal models and human patients have similar or dissimilar outcomes, is that there is a tendency for advocates on either side of the argument to cherry pick the evidence, to pick on the examples that support the argument they're trying to make. In, I think it was 2004, scientists from 3 British universities and Yale University noted that claims that animal research has been so important to the advancement of human clinical knowledge and treatment often are made only on the basis of anecdotal evidence or unsupported claims. These constitute an inadequate form of evidence, they said, for such a controversial area of research, and particularly because it is resource intensive and it consumes scientific and financial resources which are unavailable for other fields such as clinically focused research. Hence, they call for formal evaluation of existing and future animal research by systematic reviews. And that was one of the first calls for systematic reviews to be done to examine the real clinical utility for human beings of animal research as a field. That call was made in 2004 in a British medical journal. Systematic reviews are considered to provide gold standard evidence about a wide variety of clinical and research questions. They are considered to be at the top of the so-called hierarchy of different forms of evidence, ranging from the least reliable down the bottom, things like the opinions of experts, up through cases, cross-sectional studies, adding in controls, looking at entire cohorts, randomized controlled trials in which the randomization of treatments or of subjects into treatment and control groups is utilised, and finally systematic reviews to seek to locate all relevant randomised controlled trials or other forms of evidence and to jointly pool and analyse that evidence in a meta-analysis. Systematic reviews are considered to provide gold standard evidence because they aim to ensure no relevant studies are missed. They typically use multiple bibliographic databases to search for all relevant evidence in an area. If any subsets have to be examined because so many studies are retrieved, you can't use cherry picking or bias to select your set of studies. You need to use something like randomization or impartial and methodical means to select them. The inclusion and exclusion criteria for studies and evidence that you include has to be transparent. The aim is to synthesize and appraise of all good quality evidence relating to the research question, and hopefully this is done well enough that your systematic review will be successfully published in a relevant journal. Some years ago I searched the scientific literature for systematic reviews which had examined the efficacy of animal models in contributing to treatments which were efficacious in human patients. And I also conducted some systematic reviews myself in this area. At that time I found 27 systematic reviews, of which 20 had examined the utility of animal models in advancing human clinical outcomes, and 7 had looked at the predictivity of animal models for human toxicities. Of the 27, there were 3 which were particularly interesting because they sought to determine in one way or another the maximum clinical utility that might be achieved by animal experiments. I'm just going to give one example here because of lack of time. Some years ago, the head of one of the US primate research centres made passionate calls for increased funding of primate research in nature. He claimed that this research had been of critical importance during struggles against major human diseases, and that the genetic similarities between humans and chimpanzees, which are of course our closest living relatives, makes them ideal biomedical research models. So I decided to critically assess these claims, and what I did was I did a search of recent chimpanzee studies and assess the contribution of those to biomedical progress and publish my results here. Worldwide during this recent decade, I found nearly 750 studies of captive chimpanzees or their tissues. And on the face of it, they appear to have contributed to a wide variety of biological disciplines, which was great. So I went and randomly selected a subset of these. I selected 95, aimed for 105 were not able to be included because they weren't available in foreign languages or for other reasons. Of those 95, I found that about half were not subsequently cited by any publication, making little obvious contribution to the ongoing advancement of knowledge in any biological field. Around about 35% were cited by a non-medical paper and about 15% were cited by human medical papers, so maybe they made a useful contribution to treatments for human patients. There were 27 human medical papers that cited these chimp studies. With a couple of scientific colleagues, I went through them all. We found out that actually about 2/3 of these medical papers were wide-ranging reviews citing virtually everything in the field that had been of any relevance. The average number of citations was over 100 in these papers. The cited study made only a small contribution to these. In fact, no chimpanzee study cited made an essential contribution, or in a majority of cases, a significant contribution of any kind, toward medical papers describing well-developed methods for combating human diseases. And that's obviously very disappointing because chimpanzees are the species that ought to be most generally predictive of human beings. When you look at the 27 systematic reviews overall, the authors concluded that the animal models were useful in advancing human clinical outcomes or substantially consistent with human outcomes in only 10% of those studies. And the conclusion in one of the two cases was contentious because of a low sample size. 7 additional reviews failed to clearly demonstrate reliability in predicting important human toxicities, such as carcinogenicity and teratogenicity, propensity to cause cancer and birth defects, respectively. So, clearly, the animal research, animal models overall are not performing very well as predictors of outcomes in human patients. This is contrary to the widespread view within biomedical research that animal models are important and indeed essential for advancing human healthcare. So how could this be so? I think there are a number of different causes for this disparity. It's been said that the problems arise partly from the animal models themselves and also from the way in which we use them. With respect to the animal models themselves, we're talking about the interspecies differences in absorption rates, tissue distribution within the body, metabolic pathways, excretion rates of exogenous agents such as pharmaceuticals, toxins, altered susceptibility to and progression of diseases, differences in the toxicity and efficacy of pharmaceuticals. There tends to be a restriction to young animals, males, often inadequate group sizes, use of inbred strains, genetically homogeneous groups. All of these things seem to result in loss of biological variability and predictivity for more diverse groups of animals, let alone human beings. These animal test groups seem to lack concurrent illnesses that human patients often have, high blood pressure being a common example. Physiological and immunological distortions of these animal models can also result from stresses arising from their environments and the procedures that we inflict upon them. So let's look at the environments and procedures. And now we're talking about not the animals intrinsically, but the way in which these animal models are being used. Firstly, we source them from biological supply companies. The transportation chains can be prolonged. There are a variety of stressors during those transportation chains, disruption of social groupings, which can all be quite significant. There are also the stresses and other direct impacts of the procedures, which varies based on the severity of those procedures, how long they last for, and the degree to which appropriate analgesics and anesthetics are being used. A large minority of procedures are markedly invasive. These are procedures resulting in death, whether or not the animals are conscious, surgical procedures, major physiological challenges, and interference with the animal's genome. The reporting of numbers of procedures that are invasive or not varies around the world. Canada has reported them in the past. The proportion of markedly invasive procedures there has ranged from approximately 29 to 44%. Canada doesn't report anaesthetic use. Britain does. Procedures conducted without anaesthesia have fluctuated between about 59 to 69% during the decade reported there. Now, how alarming is that? Well, we need to know a bit more before drawing conclusions about that. To assess the impacts on the animals, it would be helpful to know the frequency of analgesic use as well as anaesthetic use and the degree of correlation between those procedures that are markedly invasive or result in conscious experiences and pain and anaesthetic or analgesic use, and also other factors that can affect welfare such as environmental enrichment and socialisation opportunities. However, it's hard enough to get countries to simply report animal use numbers in total. That already is quite patchy around the world. This level of additional information is often not reported at all. Recently, people have been starting to study the level of invasiveness of procedures and whether things like analgesic use is adequate. Veterinarian Dr. Catherine Herman and Professor Paul Flecknell, who's one of the world's leading authorities on analgesia in various species, recently published a series of studies in which they examined nearly 700 surgical interventions in animal research protocols submitted to German authorities for approval in 2010. In this first study, they looked at the application of health monitoring strategies and analgesia, and estimation of pain, suffering, and distress, I should say. And they found that researchers frequently underestimated levels of pain, suffering, distress, and lasting harm, and planned health monitoring strategies were often flawed. Now, the European Directive on Laboratory Animal Use and the national legislation equivalents in EU member states and others require that the severity of procedures be predicted and graded within these bands here: mild, moderate, and severe. So Herman and Flecknell went through these nearly 700 surgical procedures and actually looked at them, and they found that the vast majority were actually very invasive procedures. They were laparotomies, craniotomies, thoracotomies. They went and compared what was being done to those animals with the EU definitions of the different levels of severity, and they graded all of those nearly 700 surgical interventions as either moderate or severe, as you can see. In contrast, the researchers in their protocols submitted for approval to the competent authority graded a significant minority, about 40% of these, as being mild. Most of them as being mild to moderate or moderate, and very few of them as being moderate to severe or severe. So there's a very big difference there between how researchers were assessing their own research, proposed research, and how independent experts were assessing them compared to the EU criteria for severity. The health monitoring protocols were often inadequate. These are examples given in the publication of health monitoring protocols that can and should be applied. In this case, laboratory animal technicians should be monitoring things like body weight, breathing, mobility, and so on, and scoring all of those and coming up with an overall composite score that may trigger anything ranging from no intervention to inform the principal investigator to euthanasia. Here's another one for different types of research. Again, technicians are asked to monitor things like body weight loss, general condition, wound healing, and you can see take actions depending upon the appearance of the animals. Severe weight loss, for example, might trigger painless killing. They found, Herman and Flecknell found that the use of such health protocols for monitoring animals was often patchy and inadequate. They also looked at analgesia use in the second of their 3 studies, and they found that postoperative analgesia was not proposed for 30% of these surgical procedures. Following 10% of procedures, animals were to be given analgesics if the investigators decided this was necessary, but structured assessments to detect pain were lacking. So how did they know whether it was necessary? We know that according to good practice, surgical analgesia ought to be applied preoperatively wherever possible to prevent nerve sensitization and wind-up. You can see that in these nearly 700 surgical interventions, many of them were given preoperatively, but a lot were also given intraoperatively at the end of the procedure, or not at all. So there seems to be deviations from best practice, which are quite significant. Best practice also requires the use of multimodal analgesia where possible. We saw that this did occur for the majority of these protocols, but actually for a significant minority, this did not occur. In the third one of their studies, looking at these nearly 700 surgical interventions, experimental surgeries essentially, the investigators included humane endpoints in their application. So these are, this is the humane killing of animals when it's predicted that they're unlikely to recover, they're likely perhaps to further decline. It's thought not to be necessary to put them through any further suffering and to shortcut that via humanely killing the animals. So the investigators included humane endpoints in their application, but these were often lacking in detail and or were to be implemented at a late stage of suffering, which is not what's supposed to occur. The choice of method to kill the animals could also be improved in the majority of the applications. And the methods and agents used to kill conscious animals in one-step procedures, so that is in a single step without the animals first being anaesthetized, are listed here. And as you can see, there's quite a variety of them. Now, methods such as these are explored in detail in guidelines to best practice, such as the AVMA Guidelines on Euthanasia, which is more than 100 pages, and many of these are not in accordance with good practice or best practice for the killing of rodents. So these results are all disturbing because we are talking about recent experimental applications submitted in Germany, in the state of the region of Berlin, and we're talking about large numbers of them. We're not talking about a developing nation or a long time ago. It's likely that the practices occurring recently in Germany, in the region of Berlin, are broadly on a par with those occurring internationally in developed nations with advanced biomedical research practices. And yet so much of this is substandard. Now, what about the impacts of laboratory housing and routine procedures? Well, a review of 110 studies demonstrated or pretty clearly illustrated the impacts of the small, standardized, relatively barren caging that most laboratory animals spend most of their lives in. And this was published in Laboratory Animal in 2006. Being maintained for long periods of time in these pretty deprived environments seems to cause adverse neuroanatomical effects. So we're talking about decreased cerebrocortical thickness and weight, adverse effects on cognition and memory, adverse psychological effects as evidenced by stereotypical behavior, and I'll come back to that, and physiological effects as well. This is likely to distort results that require measurement of neuroanatomical parameters such as these, animal behavior, and some physiological parameters as well. What about enriched environments? The trouble with enriched environments is they often involve in rodent caging, Rodents, of course, being the animals that are used about 80% or 85% of the time in laboratory research. Rodent caging may be enriched by things like cardboard tubes for rodents to run through, shredded newspaper, and so on. That's still a long way short of the natural environment of the rodent, in which it has to range over a relatively wide area, finding food, avoiding predation, finding mating opportunities, seeking shelter, solving all sorts of problems, remembering potential food sources and hazards. This constitutes a lot of cognitive stimulation, actually. So compare that to a fairly barren, small cage with a cardboard tube and some shredded newspaper. And it's easy to understand, I think, why these enriched environments don't seem to prevent these adverse effects from occurring. They can delay them somewhat, maybe ameliorate them slightly, but certainly not generally prevent them. Now, what about common procedures? A review of 80 studies looking at most common laboratory species indicated that they suffer marked stress, fear, and possibly distress when subjected to not just invasive animal research, which we would perhaps expect, but more common procedures such as simply handling, blood sampling, and gavaging. And the animals don't readily habituate to these procedures over time. So what is gavaging? Gavaging is the insertion of a tube down the throat for the forced administration of a test compound orally. How common is that? It's actually pretty common. This is the routes of administration used in animal toxicity studies of the 160 compounds in the US Environmental Protection Agency Toxic Chemicals database that I studied in one of my systematic reviews previously. And amongst all these different routes of administration applied for these 160 chemicals, the most common was food, but the second most common was this gavaging method. There were some other fairly common methods that were also a bit invasive as well, subcutaneous injections, intraperitoneal injections, and so on. Now, these sorts of deprived environments and potentially stressful routine procedures are basically stressors, adverse stimuli resulting in stress. Stress, of course, is the effect on the animal resulting from stressors, which cause an alteration in their state of homeostasis. Distress occurs when the animal is unable to adapt completely to these stresses and the resulting stress and may show maladaptive behaviours. We may see physical effects such as immunocompromisation. If you look down the bottom, can be hormonal dysregulation, impacts on the immune status, immunocompetence, changes in the predisposition to disease, pathology, and of course changes in research findings that involved any measurements to do with physiology, disease progression, and so on. Behaviourally, there may be maladaptive behaviours. We may see increased grooming, self-mutilation, aggression, lethargy, and stereotypical behaviours as well. These are repetitive, apparently purposeless behaviours that are believed to indicate psychological distress, which is both profound and chronic. And this is believed to actually occur in up to 50% of laboratory-housed mice. It's often underestimated how often this occurs because rodents are largely nocturnal and observers often remain unaware of the true prevalence of these maladaptive behaviours. Another problem with how we use these animal models is in toxicity studies. We tend to use very high doses, sometimes up to the maximal tolerated doses, the doses above which severe adverse reactions would prevent further dose increases, such as vomiting, collapse, and death. So very high doses tend to be used, often for long periods of time, chronic dosing. And this works in making the test very sensitive. If something is a true toxin for humans, it's very likely to be detected as a toxic agent when you feed it to animals, rodents, at very high doses over a long period of time. The trouble is, it causes a problem scientifically. It tends to overwhelm natural biological mechanisms such as the shedding of the epithelium of the gut or the skin if you're painting toxins onto a skin surface, the overwhelming of enzymes that may be induced to break down toxins internally, DNA and tissue repair mechanisms. All of these actually might work against such toxins at environmentally realistic doses. But at these artificially high and prolonged doses, these mechanisms get overwhelmed. And so toxins that might not be toxic for humans at environmentally realistic levels are shown to be toxic in these distorted animal toxicity tests. So you get a lot of false positives occurring. So you get poor specificity of these tests for human beings, although very good sensitivity of these tests. There are also differences in rodent physiology when compared to humans. So you get increased metabolic and decreased DNA repair rates. You can get, often there are ad libitum feeding studies. This can elevate cell division rates, and elevated cell division rates can predispose to mutagenesis, potentially even carcinogenesis. And then there's another problem as well, which is widespread within animal research, and that is the problems with the methodological quality. So we're talking about the design, conduct, and reporting of animal research. Many systematic reviews, 11 in the set that I initially found and many more since then, have demonstrated common methodological flaws within animal research. None so far have looked at any sizable group of animal experiments that have been published and found the majority to be of good methodological quality. Common deficiencies are lack of sample size calculations, instead arbitrarily picking numbers, lack of sufficient sample sizes so that we get small numbers of animals that can't reliably predict what occurs to the wider population of the same species, let alone for human beings. Lack of randomization during the allocation of animals to different treatment and control groups. Lack of blinding during the assessment of outcomes, and I'll come back to that in a moment. And lack of conflict of interest statements as well, which we need to look at when we're interpreting published papers. Now, sometimes blinding during the assessment of outcomes is, of course, not necessary. Sometimes it's easy just to look at results, and it's pretty unambiguous where there has been a change or an effect. Other times it's much more subtle. Often we will occlude cerebral arteries, generating areas of ischemia within the brain, so artificially induced focal ischemias, i.e. stroke models. And we will give test animals a test drug to see, and we'll give no test drug to the control animals. We kill them both, we section the brains, we look at the slides under a microscope. We want to see whether the area of devitalized tissue, this white area, this infarct, has been reduced in size in the animals that have received the test drug. In other words, whether there was any beneficial effect. Now, in the middle, it's easier to see that this area is white. Well on the outside, it's easier to see that this is normal brain tissue. But what about the grey zone? What about the margins all the way around? Here, we're looking at something much more prone to error than a clear-cut fracture X-ray. Biases in the interpretation of results seem to occur more commonly when people are expecting to see a certain result, when they're measuring these sorts of subjective variables, and then when they've got an incentive to produce data that confirms their predictions. The study of bias within research protocol has become a fascinating field in its own right. Biases are systematic errors that result in errors in the interpretation of research results. And they may occur at different stages in a research protocol. For example, in the beginning, a researcher may look at an animal and decide that this animal looks a little bit weaker than the others and may have a conscious or unconscious sympathy toward that animal, may choose to pop it into a control group rather than undergo a test procedure. Suddenly, the research results no longer reflect the efficacy of the test agent alone. They're now being influenced by unequal biological fitness. So the way to eliminate that is via randomization of animals in their allocation to treatment groups and control groups. Performance bias is a systematic difference in the care provided to different animal groupings. And again, you can deal with that by blinding the people, not literally obviously, but making sure that they're not aware of which animals they are treating, whether they're in treatment group A, B, C, or a control group. Detection bias occurs as in the previous example, where somebody might be looking at slides of a brain and think that they're seeing something that's not there. And the way to deal with that again is to make them unaware of whether the animal has undergone the test procedure or not. So blinding them to whether the animals are in a placebo or control group, essentially. Attrition bias occurs when there is unequal treatment of animals that are lost to the study for one reason or another. How common are these sorts of bias within animal research protocols? Here is a study in PLOS Medicine 2010 looking at systematic reviews of animal models in different fields of human healthcare. You can see the fields in the left-hand column: heart failure, ischemic stroke, traumatic brain injury, many others. In the fourth column, we're looking at the percentage of the studies in each group that used randomization for allocation of animals to treatment and control groups. We should be seeing close to 100% here. We're seeing 67%, 32%, 42%, and a lot with lower numbers than that. What about the next column, the blinded assessment of outcomes? Again, we should be seeing 100%. In the first group, we did see 100%. That's great. That was heart failure. But all of the remaining groups, we're getting 11%, 40%, 12%, and low numbers. Prior calculation of sample size, a statistical justification of sample size, in other words, very infrequent. So sadly, these sorts of errors within the design of scientific research using animal models are very prevalent. What are the effects of not including such steps to eliminate any risk of unconscious bias in the interpretation of research results and the design of research protocols? We know from other fields that these effects can be quite significant. Reviews of animal research in the field of emergency medicine, estimates of treatment efficacy were significantly reduced in studies that incorporated randomization and blinding. Similar results from numerous other fields. In fact, studies that incorporated the fewest measures to minimize sources of bias also reported the greatest effect sizes. What does that tell us? It tells us that when people think they're seeing large effect sizes, they're probably not. And these are probably artifacts. They're not truly occurring biologically. They are a result of us, of what we're doing as interventionists and as observers. In recognition of these dangers, Kilkenny and colleagues published in 2010 a set of guidelines, the Animal Research Reporting for In Vivo Experiments Guidelines. And these are designed to ensure that these sources of bias are minimized as far as possible. They describe the steps that ought to be taken to do things like justify sample sizes, allocation of animals to different treatment and control groups during the assessment of outcomes, and indeed at every stage throughout the design, conduct and reporting of animal research. And there have been other similar guidelines published by others. This one here describes 74 items that should be incorporated to ensure the scientific quality of animal research, fully integrate 3Rs methods, facilitate their incorporation within systematic reviews, and so on. The trouble is that follow-up studies have shown that the compliance of animal researchers with these guidelines, these sorts of guidelines, remains poor. Even though the arrived guidelines, which are the best known, have been published or endorsed by over 1,000 research journals and major funding agencies, a follow-up study of all licensed animal researchers in Switzerland recently reported that among 16% of those who chose to participate and ought to have been most engaged with studies into standards of animal research and best practice in animal research, 56% didn't know of the arrived guidelines, and even among those whose latest paper was published in a journal that had endorsed them, 51% had never heard of the arrived guidelines. So that's pretty scandalous, quite frankly. That's absolutely not okay. Now, let's say that we somehow managed to overcome the interspecies barriers to extrapolation of animal results to human beings. That was the first problem. Let's say we managed to fix up all of the other problems to do with poor scientific quality, the way in which we use animal models to stress them and essentially distort the research results that we measure from them, which seem to result in the reproducibility crisis that plagues animal research, the difficulty in reproducing research results in subsequent animal studies. Let's say we fixed all that up through some kind of widespread transformative change to the animal research field. One major problem would unfortunately still remain, and that's the problem of publication bias, sometimes also referred to as the file draw problem. And the best way to illustrate that is to consider something like a test drug given to a group of mice. Let's say that the test drug actually has no biological effect. Let's say we repeat that experiment 20 times. 19 times out of 20, let's say we get no effect of this drug. But because of random biological variation, let's say that one time in 20, it appears that the drug is producing an effect. It's not really an effect, it's just the random biological variation of that particular group of mice. So it's actually a false positive. The trouble is that false positive is considered to be more exciting by journal editors, reviewers, and readers, meaning that that particular study is more likely to be published in a scientific journal. And in the extreme case, the 19 studies that truly showed no effect end up in somebody's file drawer and are never published. The one study that falsely demonstrated an effect went on to be published. And later on, when somebody like me or anybody else comes along to do a systematic review and searches the published literature for every piece of evidence relating to the test drug, they'll find that one study, they'll miss the 19, and they will draw false conclusions about the effectiveness of that drug. So, how common is this problem within animal research? People have been starting to study this as well. Senna and colleagues published an analysis of this problem looking at animal models of stroke. They looked at 16 systematic reviews of different putative interventions that it was hoped would help stroke patients. These involved over 500 publications, nearly 1,400 experiments, about 6,000 animals. And you can see the interventions there: estrogens, growth factors, melatonin, many others. You can see the reported effect sizes on the right-hand column. In these systematic reviews, we had 26% for the first group, 32%, 29%. Overall, they all seem to be quite large, and the pooled analysis was 30%. Out of these more than 500 publications, there were 525, only 10 of them reported no effect. So alarm bells should be going off here. That's not very likely at all, given that none of these are so far proven to be effective. For each one of these, they conducted statistics. This is one of these interventions. You can see that all these individual animal experiments have come up with a certain effect size. Most of them are clustering around an effect size of 25 in this particular example in the top chart. Because of random variation, you'll get a certain proportion of them come up with a higher effect size, some have a lower effect size, and they should deviate equally from the central point. However, you can analyze this apparent funnel plot statistically, and when you do that, you get the bottom funnel plot. You discover that in order to generate statistically as close as you can to a perfect bell curve, you have to add in a whole bunch of red dots down in the bottom plot. Those red dots actually represent missing experiments which were never published in the literature, unlike all the black ones which were published. And when you add in the red dots, you are able to generate something like a perfect bell curve. So they went through this, and they did this for all of these systematic reviews with large numbers of studies looking at the effectiveness of these 16 different agents for treating stroke. And they found that once they added in the missing experiments that they would calculate must have been there statistically, it resulted in a changed overall estimation of effectiveness for each of these agents. Overall, the effectiveness dropped from 31% down to 24%. They estimated that 1/6 of animal experiments had not been published, and that this involved the lives of 3,600 animals. So those lives were consumed. They did not contribute to any published outputs, and as a result, systematic reviews finding all the evidence in the area failed to find the unpublished results and resulted in overestimations of the effect size for all these test agents. They concluded that it's probable the publication bias has an important impact in other animal disease models and more broadly across the life sciences. So, when we're asking why do animal models not better predict human beings, as has been demonstrated in all of the systematic reviews that have looked at this, the reasons are because of the differences between animal models and human beings intrinsically, the barriers to extrapolation of results to humans, also because of the ways in which we use the animals, the distortion of these animal models through stresses of various kinds, chronic high doses, also scientific flaws in the design, conduct and reporting of animal research, introducing systematic biases. And finally, after all of that, the focusing on positive results, the insufficient focus on negative result, the problem of publication bias. So we get a false understanding of how truly effective a test agent actually is in mice, let alone in any other species. So, the historical and contemporary paradigm has been that animal models are fairly predictive of human outcomes, and this is the basis for their widespread use in toxicity testing and biomedical research aimed at developing cures for human diseases. But their use persists for historical and cultural reasons rather than because they've been demonstrated to be scientifically valid. But most systematic reviews, when they've been done, have demonstrated that animal models are actually not sufficiently predictive of human outcomes to offer substantial benefit during the development of clinical interventions or human toxicity assessment. Consequently, we can't generally assume that animal data is useful for these purposes. Of course, there are other impacts that are important. This research consumes substantial financial, personnel and scientific resources which are unavailable for more clinically focused research on human patients. So when we come back to that initial utilitarian harm-benefit analysis that's supposed to underpin and justify animal research in general, when considering the costs and benefits overall, I don't think you can reasonably conclude that the benefits accruing to human patients or consumers, or those motivated simply by scientific curiosity or profit, exceed the costs incurred by the animals subjected to these procedures, which, as we've seen, are quite substantial. And there are many millions of these animals being experimented on around the world each year. On the contrary, the evidence indicates that actual human benefit is rarely sufficient to justify these costs. And the more speculative the human benefit becomes, as in the case of fundamental research rather than clinically applied research, the more obvious the resultant disparity. In fact, it's only possible to reasonably conclude that this research is ethically justified if you use a profoundly unequal weighting, in which you say that relatively minor or infrequent human benefits are more important than the significant adverse impacts which are commonly experienced by laboratory animals. So, what does this say about ethical oversight? Well, the approval of very large numbers of these sorts of experiments, despite their questionable merits, demonstrates a widespread failure of ethical oversight. By approving these experiments on the basis of unfounded assumptions about their likely benefits, the ethics committees responsible have failed in their duty to society and to the animals they're charged with protecting. My research in this area is at my website animalexperiments.info, and for those interested in this subject further, I highly recommend this recent entirely open access textbook, Animal Experimentation Working Toward a Paradigm Change, by Catherine Herman, who I mentioned in this presentation, and Kimberly Jane. It has an updated chapter of my own, all about the latest evidence from systematic reviews of animal research. And of course, there's my earlier book in this topic as well. Thank you very much.